Hi everybody, I hope this video finds you well. In today's video, we're going to do a quick summary of the hypothesis test and confidence intervals that we've covered in our course. We've been studying hypothesis tests and confidence intervals now for about 6 weeks, so we've learned a lot of them, 8 hypothesis tests and 5 different confidence intervals. So we're going to talk a little bit about some identification techniques to help pick out the appropriate hypothesis test or confidence interval for a given situation, and then we're going to also talk a little bit about the key features of each hypothesis test and confidence interval. So let's get in first by talking about the hypothesis tests. So for hypothesis tests, you guys did learn 8 different hypothesis tests. But before we can start talking about how to identify the appropriate hypothesis test for a given situation, we need to talk about a major classification. We separated our hypothesis tests into ones that apply to quantitative and categorical data. So let's imagine that separation first. So we had some that applied to quantitative data, and we had some that applied to categorical data. And again, that's why at the very beginning of our course, we spent so much time talking about the difference between quantitative and categorical, because it's so important for identifying the appropriate inferential statistics, the appropriate hypothesis test, if we can distinguish between quantitative and categorical. Hopefully, at this point in the course, you guys are comfortable reading a variable and understanding if it is quantitative or categorical. But if you're ever unsure, remember there's a few sort of keywords that you can use to help you make that decision. If you see any mentions of words like average or standard deviation, then those key you in that you're talking about something that's quantitative. Only for quantitative variables to do concepts like average and standard deviation make sense. Things like percentage or proportion or distribution, those are all terms that if you see those mentioned, indicate that you're talking about something categorical. We work with percentages and proportions as our main measures for categorical variables, and distribution is something that often references the distribution of a categorical variable. So if you see any of these types of terms, you can use those to key in on whether or not you're talking about something that is quantitative or categorical. So let's talk a little bit about the types of hypothesis tests that we have for quantitative information. So for quantitative information, we learned 4 different hypothesis tests. So we'll sort of give ourselves 4 different pieces here, and let's talk about what each of those were. The very first type of hypothesis test, this was the first one we ever learned in our course, right, was a one sample mean hypothesis test. Then we also talked about the 2 sample mean hypothesis test, the matched pairs, and most recently, we introduced our final quantitative hypothesis test, the ANOVA hypothesis test. So these are the 4 different procedures that you might apply when you have quantitative data. How do we distinguish between these? Well, remember that as the name would apply, a one sample mean hypothesis test is one sample versus a known average. So when you're planning on running a one sample mean hypothesis test, the situation you should be in is that you have a single sample that you want to compare against a known or assumed average. A 2 sample mean hypothesis test is when you have 2 samples from 2 populations. So remember, 2 sample procedures are generally used when you have 2 samples from 2 separate populations. So maybe you want to compare the average for men for some variable against the average for women for some variable. Or maybe you want to compare the average for some variable for adults in the US versus the average for that same variable for adults from a different country. That would be the type of thing you would use a 2 sample mean hypothesis test on. Matched pairs is a very specialized test. It only is used when you have matched pairs data. And remember, generally, that means that you should have data that comes in the form of a test 1, test 2 structure so that you actually know how the individuals were matched. Now, again, it doesn't explicitly have to be test 1, test 2. It could be a before or after, something along those lines. But you have to know how you're matching the individuals. You have to basically know what score or value did people have initially and what score or value did they have later. ANOVA, well, that's our most recent one. That was sort of an extension of the 2 sample mean. This is when you have 3 or more samples from 3 or more populations. So the ANOVA test basically extends our logic from the 2 sample mean hypothesis test to 3 or more samples. So the way you should sort of view our quantitative section is we've got things for 1 sample, 2 sample, and 3 or more samples, and we have this very special subcase of when we have matched data. All right, let's turn our attention now to the categorical side of things. Again, remember keywords for categorical are things that mention percentage, proportion, or distribution. So for categorical, you guys also learned 4 different hypothesis tests. So let's talk about what those were. Well, we started with what we called the one sample proportion hypothesis test. We also discussed what we called the 2 sample proportion hypothesis test. Then we learned a couple of global hypothesis tests based on a different distribution called the chi-squared distribution. We learned the chi-squared independence and homogeneity, and we also learned the chi-squared goodness of fit. So those are the 4 procedures that we learned that apply to categorical information. So how do we identify these? Well, a one sample proportion hypothesis test is very similar to a one sample mean. It's going to be where you have one sample versus a known percentage. So we'll put a little dividing line here just to make that a little bit easier. So this is a one sample versus a known percentage. So when you're doing a one sample proportion, you have a single sample versus a single known percentage. Remember also that this has to be Boolean, meaning that we apply this one sample proportion hypothesis test only when we have a Boolean categorical variable, meaning a categorical variable that only has 2 categories. A 2 sample proportion hypothesis test is when we have 2 samples from 2 populations. And again, the data is supposed to be Boolean. So for both a 1 sample proportion and 2 sample proportion, it has to be categorical, but it specifically has to be Boolean categorical, where you only have 2 categories. Chi-squared independence and homogeneity, this one is very specialized and unique. This is where you want to know if there's a relationship, and that's a key phrase there, between 2 categorical variables. And remember that this guy also has a nice easy way of identifying just by looking at the data. This means that we should have a two-way table as our way of holding or presenting the information, because the way that you display information related to 2 categorical variables is in a two-way table. So if you see a two-way table, you know you're doing that chi-squared independence and homogeneity. Finally, for chi-squared goodness of fit, this is about the distribution of a categorical variable. So if you see anything that mentions whether or not a distribution has changed or is different, so in other words, if you see that keyword of distribution, then you know you're supposed to use a chi-squared goodness of fit. So there we go. There's our 8 different hypothesis tests divided into 4 that apply to quantitative information, 4 that apply to categorical, and a little bit about how to identify each of them. Let's do the same thing for confidence intervals. Now it's a little bit easier with confidence intervals because we have fewer of them. So let's go ahead and talk about confidence intervals. For confidence intervals, we can once again do our same separation. We can talk about confidence intervals that apply to quantitative data and ones that apply to categorical data. Again, quantitative, you can identify usually by seeing words like average and standard deviation. Those terms only apply when you have quantitative information. And for categorical, you should again be expecting percentage, proportion, distribution. That helps us identify categorical information. What types of confidence intervals do we have for quantitative data? Well, we actually had 3 for quantitative. We had 1 sample mean confidence interval. We had a 2 sample mean confidence interval, and we had a matched pairs confidence interval. For categorical, we only had 2. We had a 1 sample proportion confidence interval, and we had a 2 sample proportion confidence interval. So let's talk about what each of these 5 procedures is used to do. Remember, all confidence intervals exist to help you estimate some unknown population parameter. So as we describe each of these, it's always going to be about estimating something. So here you want to estimate an average of a population. So if you want to just estimate a single average of a population, you want to use a 1 sample mean confidence interval. If you want to estimate the average difference between 2 populations, then you want to use a 2 sample mean confidence interval. And if you want to estimate the average difference from matched pairs data, then you would, of course, use a matched pairs confidence interval. So what this should basically tell you is, once again, the matched pairs confidence interval, very special, sort of unique. Only use it if you have matched pairs data. For identifying between one sample and two sample means, well, keep in mind one sample means are used to estimate an average, while two sample means are used to estimate an average difference. So if you can keep that in mind, that one is for averages and one is for average differences, then you can always distinguish between one sample and two sample mean confidence intervals. The same trick applies for one sample proportion and two sample proportions. This guy is used to estimate a percentage for a population, and a two sample mean or a two sample proportion confidence interval is used to estimate the difference in percentage between two populations. So there we go. We now know again what are their categorical confidence intervals doing. They're always trying to estimate a percentage. One sample proportion is if you want to estimate a single percentage. Two sample proportion is used if you want to estimate the difference in percentage. Okay, now we're going to do a brief summary of the key features of each hypothesis test and confidence interval. Now, as we begin to do this summary, keep in mind I'm not going to rewrite fully all pieces of every test and confidence interval. If you need to reference any of the details, you can always go back to their corresponding videos where they were introduced and look those over. But I just want to sort of give you guys a sort of condensed summary so you understand exactly the most key and most different features of each hypothesis test. So let's go ahead and look at that. So let's start with our one sample mean, and we'll try to fit about 2 tests per one of these pages here. So if we talk about the one sample mean hypothesis test, so we'll sort of go down the steps one after another, indicating the most important features here. So keep in mind that for the hypotheses, the format here is mu equals something, and the null mu with a greater than, a less than, a not equal to, and that same value. For 2, conditions 1 and 2, random and representative, sample size less than 5% of the population size, that applies to all of our hypothesis tests. So let's just focus on condition 3, which is the one that varies from test to test. Here, remember, it's either that n is greater than or equal to 30, or data approximately normal. Let's talk about the test statistic. Test statistic here is t equals x bar minus mu over s over root n. That means that when you do the p-value step, you need to use table C with degrees of freedom equal to n minus 1. And remember, you use one-sided / two-sided based on HA, right? Based on your alternate. Do I need to say anything about step 5? No. Why not? Because step 5, making the conclusion, is the same for every hypothesis test. P-value less than alpha, reject. P-value greater than alpha, fail to reject. So these 4 pieces here show the things that are most unique about the one sample mean hypothesis test. Let's talk about the two sample mean hypothesis test. Well, hypotheses here, mu1 equals mu2, always. And the alternate, well, you can choose that you think one is smaller, greater than, smaller than, or simply not equal to the other. For condition 2, we need n1 greater than 30, n2 greater than or equal to 30, or both data sets approximately normal. For step 3, you would have a test statistic that would look like x1 bar minus x2 bar over the square root s1 squared over n1 plus s2 squared over n2. And for step 4, when you go to use your table C, your degrees of freedom, remember you use the minimum of n1 and n2, you use the smaller one, minus 1. And of course, you still do one-sided / two-sided based on HA. Again, are we omitting some things? Yeah, didn't mention conditions 1 and 2 because those are always the same for every hypothesis test. Still got to check them, but don't need to rewrite them as key features, right? Because you guys already know those. Again, also not saying anything about step 5 because that's the same for every hypothesis test. All right, let's talk about some other ones then. I'll go ahead and put these guys right here. Our matched pairs hypothesis test. Remember that when we do this, our data is actually the differences, right? Everything is going to reference the differences. So when you go to step 1, your null and your alternate, you're going to use the D equals and D greater than, less than, or not equal to. Same language, these guns greater than and less than would be one-sided, not equals to would be two-sided. For condition 3, right, it would either have to be that your sample size is greater than or equal to 30, or the differences would be approximately normal. Again, when doing matched pairs, everything is about the differences, not about the data from test 1, not about the data from test 2, but about the data in the differences. For step 3, it is still a T statistic. It would be D bar minus D over SD over root N. Again, all these things, D bar, SD, just represent the average and the sample standard deviation of the differences. Then, 4, we would still go to table C, still use degrees of freedom equal to N minus 1, and then one-sided / two-sided based on HA. Okay. All right, there's our matched pairs. Then the last sort of one that we discussed for quantitative information was the ANOVA hypothesis test. Here, the hypotheses, the null, is going to be that every population average is going to be equal. Remember, there's going to be at least 3, perhaps more. And the alternate is that at least one population average is different. Remember that the ANOVA hypothesis test is an example of a global hypothesis test, meaning that its alternate doesn't say what that difference is, it just says that there is a difference. In step 2, we've got a couple special conditions. For step 3, all sample sizes need to be greater than or equal to 30, or all samples need to be approximately normal. And there is a fourth condition that you need to check, which is that you check that the maximum sample standard deviation is less than 2 times the minimum sample standard deviation. This actually confirms a more general condition that the population standard deviations are not too different. But we do that by checking that the maximum sample standard deviation of all the samples is smaller than 2 times the minimum one. Then also remember that steps 3 and 4 here are done for you by using your stat, tests, and then ANOVA, and then doing ANOVA of L1, L2, L3. If there's any more, you need to put those and then close up that parentheses, and there we go. So that's our ANOVA test. So right here, we have all 4 of our quantitative procedures, just focusing on the pieces that are different from each of them. Now let's turn our attention to the categorical ones. So we'll start by talking about the one sample proportion. So the one sample proportion hypothesis test. The hypotheses here, we write them with P equals as our null, and our alternate is P greater than, less than, or not equal to. Remember that here, we don't just say one-sided and two-sided. We would say that this is right-sided, this is left-sided, and this is two-sided. So we have to be a little more careful because we're going to be using table A, and we need to know if we need to do anything like 1 minus or anything like that. For 2, the only condition we got to worry about that's different from each one is condition 3. Remember, this is where we check NP1 minus P greater than or equal to 10. For 3, it'll be a Z test statistic, and it's P hat minus P over the square root, P1 minus P over N. Only thing we should probably note here is a reminder of how we calculate P hat. Remember, P hat is the number of successes divided by the sample size. Then for step 4, the p-value, you would be using table A and direction of HA. Remember that if you have a right-sided test, you'll look up the z-score on table A and then do 1 minus the result. If you have a left-sided, well, you can just use what you find on table A, and if you have a not equals to, you'll have to find what's to the left and then double that value. So you got to be a little bit careful here and look at the direction of that alternate. All right, let's talk about a two-sample proportion hypothesis test. For the hypotheses, just like the two-sample mean, the null is always that the two population proportions should be equal, and the alternate allows you to have the choice that one is greater than, less than, or simply not equal to the other. Condition 3 is a bit different. It's that you have to have at least 5 successes and 5 failures in both samples. So we need the successes and failures in each to be greater than or equal to 5. The test statistic is still z. It's p1 hat minus p2 hat, but the denominator is a little messy. It involves that p tilde, which is actually the pooled sample proportion, and then 1 over n1 plus 1 over n2. As a little reminder here, p1 hat would be found as s1 divided by n1. P2 hat would be S2 over N2, and that P tilde is found by pooling the successes together and then dividing by the sum of the sample sizes. So probably one of the more complicated test statistics, but there we go. And step 4, also table A and direction of HA. So there we go. There's our one sample proportion and our two sample proportion hypothesis tests. All right, let's go ahead and talk about the chi-squared ones, wrapping up our discussion of hypothesis testing here. So we have chi-squared independence and homogeneity. Remember that the hypotheses here, this is one that we write out more in words than mathematically. We would say that the variables are not related. That's always our null. And our alternate is always that the variables are related. So remember, when we are doing a chi-squared independence and homogeneity, we're talking about whether or not there's a relationship between two categorical variables. Our default view is that the variables are not related, and our claim is that they are related. Then, remember, we have an intermediate step. So we have to get that expected counts table. That expected counts table, those expected counts are calculated as doing the row total times the column total over the table total. And you'll need to do that for everything in the two-way table so that you can get those expected counts, and that's a multiplication in between those. Then you can move on to the conditions. Condition 3, again, is the sort of special one. We have to have less than 20% of the expected counts can come in less than 5. If all of the expected counts are greater than 5, then this guy is trivially going to be true, but you just got to make sure you can't have too many small expected counts. Then the test statistic is a bit different. It's a chi-squared test statistic, and we find that by taking the sum of the observed counts minus the expected counts squared over the expected counts. Remember, the expected counts are what you calculate in that intermediate step, and the observed counts are your actual data. And then for step 4, you go on to table D, and you use your degrees of freedom, which is going to be the number of rows minus 1 times the number of columns minus 1. So it's basically based on how many options you have for your first variable and how many options you have for your second variable. Multiply those together, and you get your degrees of freedom. All right, last hypothesis test, the chi-squared goodness of fit. Remember that here this is about the distribution, so the null is what we originally assumed the distribution would be. So P1 equals, P2 equals something, P3 equals something, and so on. There's going to be at least 3 categories here because chi-squared goodness of fit steps in when we don't have something that is Boolean, which would only have 2 categories. So there's going to be at least 3 things here, maybe more. The alternate is going to remain global, so it's going to say at least one proportion has changed / is different. So we're saying at least one proportion has changed or is different than we originally thought in that null hypothesis. We get our expected counts by doing n times pi. So what we do is we take the sample size and we multiply it with each of the null hypothesis proportions. Then step 2, condition 3, same thing, less than 20% of expected counts less than 5. Step 3, Same thing, chi-squared, same formula, observed counts minus expected counts squared over expected counts. Step 4, table D again. Only a little difference here is the degrees of freedom is just simply the number of categories minus 1. So that right there summarizes all 8 of the hypothesis tests, again, focusing on the features that are different for each test. All right, let's wrap up this summary by talking about the same thing for the confidence intervals. So for the confidence intervals, we're going to start by talking about the one sample mean confidence interval. The conditions, same as hypothesis test. So the same conditions for the hypothesis test, the one sample mean hypothesis test, apply to the one sample mean confidence interval. The actual construction then is x bar plus or minus t star s over root n. And remember that t star is going to come from that table C, degrees of freedom equal n minus 1. So you intersect that confidence level and your n minus 1, and that'll give you your t star then. The two sample mean confidence interval, this guy also has same conditions as the hypothesis test. The construction for this guy is x1 bar minus x2 bar plus or minus t star square root s1 squared over n1 plus s2 squared over n2. And this guy also has t star coming from table C, where you'll have your degrees of freedom being the minimum of n1 and n2 minus 1, and you'll intersect that with your confidence level, and that'll give you t star. Let's just go back real quick and draw out that same diagram here just because it looks nicer, right? So this t star here comes from table C, confidence level, and your degrees of freedom being n minus 1. Intersect those, that'll give you t star. So there we go. There's our one sample mean confidence interval and two sample mean. Same conditions as their corresponding hypothesis tests, and those are the construction formulas. We also have our matched pairs confidence interval. Okay. Same as hypothesis tests for the conditions. All of the quantitative confidence intervals have their same conditions as their corresponding hypothesis tests. Then the construction, d bar plus or minus t star, sd over root n, t star, again from table C, degrees of freedom, n minus 1, confidence level, intersect those together, that's going to be your t star. So that right there summarizes your 3 quantitative confidence intervals. Let's wrap all this up with talking about the proportion-based ones. So, first one for the proportions is we've got our one sample proportion confidence interval. Remember, this guy actually does have a different condition 3 than its hypothesis test. Its hypothesis test has that NP1 minus B needs to be greater than or equal to 10. Condition 3 for a one sample proportion confidence interval, though, is that the successes are greater than or equal to 10 and the failures are greater than or equal to 10. So in other words, we have at least 10 observed successes and at least 10 observed failures. Then for the construction, it's p hat plus or minus z star square root p hat 1 minus p hat over n. And that z star, again, does come from table C still, but you'll just use z star, intersect that with your confidence level, and that'll give you your value there. So not too bad to be able to do that guy. Last one, two sample proportion confidence interval. This guy does have the same conditions as his corresponding hypothesis test. So only the one sample proportion has a different third condition. The construction here is P1 hat minus P2 hat. That's your point estimate, plus or minus Z star square root P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2. Again, Z star, same idea. Table C, confidence level intersected with the Z star row will give you that Z star. Now, One other thing besides my last sort of comment about this whole summary is I hope you guys also see what this sort of tells you, the whole idea of why we spend so much time talking about this stuff. Even though there's a lot of stuff here, I mean, we just did about 4 pages of stuff. This summarized 6 weeks of material into these just 4 pages. Because really, the whole idea between hypothesis testing and confidence intervals is that this is a way of statistical thinking. Each test in each interval, yes, it works for different situations and estimates different things, but the structure, the logic behind it is the same. Every hypothesis test runs on these 5 core steps. Every confidence interval runs on these core 2 steps. And that even extends to hypothesis tests and confidence intervals that we don't talk about in this course. So really, you guys have learned a form of statistical thinking here. And hopefully this summary, not only is it beneficial for helping you guys sort of do that identification and solve, particular questions, but it really shows you guys that sort of power of the statistical thinking that you've learned in this course. That's going to do it for our class. So this is the end, signing off.